There's an underreported radiation protection risk in the widely used technique of ultrashort pulsed laser machining. But what do we mean by that?
Ultrashort means a pulse duration less than 100 picoseconds down to a few femtoseconds. As an illustration, light travels 300,000 kilometers per second, but it only moves 0.3 micrometers in 1 femtosecond.
Only a few years after the invention of the laser, first attempts to generate ultrashort laser pulses were successful. The initial idea was to monitor natural processes at very short time scales, like a very fast camera. Soon, higher laser pulse energies made it possible to process materials in new ways.
The low heat load of these intense laser pulses enables a melt-free machining of almost all workpieces. With increasingly powerful systems, this technology found its way in microfabrication and enables the production of highly precise parts in an industrial scale.
In laser material processing, a focused laser beam is directed towards the sample surface. The resulting high intensities of the pulses can ablate the material, and this results in an ablation crater on the material surface. When irradiating millions of pulses to the samples, higher volumes can be removed. The pulse repetition frequencies ranges typically between kilohertz and megahertz. For large area processing, the laser beams are raster scanned over the sample surface by using a line-by-line and layer-by-layer scan regime. The laser beam moving speeds can reach several tens to hundreds meters per second. Depending on the relative movement between the laser beam and the target, the ultrashort pulses can be used for fine cutting, laser drilling, micro engraving, and surface texturing.
If an ultrashort laser pulse is focused tightly onto a workpiece, extremely high laser intensities exceeding 10 to the power of 13 watt per square centimeter can be achieved. This causes material removal along with optically visible plasma emission. Additionally, unwanted secondary radiation can be generated. Depending on the material and the laser parameters, energies up to the X-ray level can be generated.
The X-ray photon emission spectrum includes continuous Bremsstrahlung as well as characteristic X-rays. So far, a maximum of 40 keV was detected for the laser-induced X-ray emission during materials processing in air. Close to the laser interaction zone, we measured 1 sievert per hour for the skin dose rates.
Generally, higher laser intensities leads to stronger X-ray emission. Currently, projects are running to determine the threshold of X-ray emission. Furthermore, burst pulses are more critical than single pulse use.
Dielectric materials, such as glass, show very low X-ray emissions, whereas the processing of metals can cause very high X-ray emissions. Steel and tungsten are particularly critical.
Ultrashort pulsed lasers are also used in medical application. We discovered that X-ray emission can be generated during the laser-based processing of biological materials. Recently, the highest X-ray exposure was found during the processing of teeth. At BAM, the Federal Institute for Materials Research and Testing, we currently run a project funded by the Federal Office for Radiation Protection to investigate the possible emissions resulting from ultrashort pulse laser pulses in dentistry.
In Germany, we have 3 categories for laser operation depending on the laser irradiation conditions. First, without any notification and approval. Second, official notification. And third, license for operation. An efficient solution to protect against this risk and hazards is to enclose the laser processing area with a 2 mm thick stainless steel housing.
We at the Federal Office for Radiation Protection, the BFS, have been included in radiation protection for ultrashort pulse laser systems since 2018. In 2022, this led to the inclusion of these ultra-short pulse lasers in the Radiation Protection Act as devices for creating ionizing radiation. The BFS and the BAM are working closely together on the laser-induced X-ray generation problem within the framework of research projects. It is important to understand the mechanism behind the generation of X-rays during the use of ultra-short pulsed lasers for material processing, so that we can make sure that radiation protection is always adequate, no matter what material is being processed and what lasers are being used.
Interestingly, the average power of ultra-fast lasers follows a type of Moore's law, leading to a doubling of the average power every 2 to 3 years. The availability of high repetition rate laser sources and novel beam delivery concepts will boost the possible application in materials processing with respect to workpieces and processing efficiency.
For this purpose, further research projects will be key, so that we can be at the forefront of radiation protection for future systems. With the regulation introduced in 2022, a lot of these laser machines have been brought under regulatory control in Germany and now have a satisfying radiation protection regime. I'm sure we're heading in the right direction. However, this issue still needs the attention and action of all international stakeholders to ensure appropriate radiation protection in this industrially highly relevant and dynamic field of laser application.